Welcome, everyone. Thank you for joining us this Thursday for our webinar. Before we get started, I just wanted to go over some helpful areas that you should see on your console for the webinar. We will have a Q&A portion at the end of this webinar, so please feel free to ask questions at any point through the Q&A feature that can be found to the right of your console or down at the bottom. We also have a survey that you can fill out with any feedback regarding today's webinars or topics you would like to discuss on future webinars. Please also take a look at our resources over on the left side of your console. These resources, in addition to the final presentation, will also be emailed to you tomorrow, so be on the lookout for that. I'm going to pass it on to Nancy, who will introduce our speaker for today's webinar. Thank you.
Oh, thanks, Caitlin. Yes, welcome to our webinar, Chemistry Hour Series with Guy Boisvert, Pre-Analytical Challenges Part 2, in case you missed Part 1. I am pleased to introduce our presenter, Guy Boisvert, our Clinical and Forensic Chemistry Account Manager for the U.S. and Canada. Guy brings more than 28 years of experience at Waters with his immense expertise in chemistry product selection and post-sales support. Guy's mission is to help you save valuable time in method development by ensuring you start with the right product from the outset. And now, please join me in welcoming Guy. Take it away.
Thank you, Nancy. Today we will just review a couple of things that will be important, I think, when we think about how you work, mainly to find new methods for something. You will definitively go into the application notes. You will go into the literature. You will find some sample preparation and some method where they describe the column they take and everything. And I've asked many people what happened when you transfer the method in your lab. And this is where sometimes it doesn't always work. So the topic today will be to make sure that what you see in the literature will transfer to your lab more easily. So we will review the theory, the background a little bit. So it's very important to cover them because this will be the foundations for the rest of the seminar. And then we will look at the method transfer calculation itself. That portion will be the theory. So you will need to see, or you will be able to see how it's done, but you won't need to remember the formula and everything. It won't be complex because we have a tool called the calculator, the Acuity column calculator, that will do all the job for you, all the calculation. But it's important to understand what's happening for those calculations. Right now, the calculator has been removed from the website temporarily because we are coming with a new version that should become available within the next few weeks maximum. So you will be able to go to our website in the support tab, and then under the support, you will be able to see the tools and calculator, and this is where you will find the calculator for the one we will see today. Okay, let's start with the questions. I will ask you a few questions during the seminar, and I will always prepare the questions before we cover the material. So right now, I'm not expecting you to know the answer directly, but this is something we will cover in the next sections. If you want to get more retention, what can you do? Can you use a longer column to get more retention, change the mobile phase and or stationary phase, decrease the flow rate, or all of the above? So take a few seconds to answer those questions, that question, please. It will give me like a kind of background of if I should spend more time or less time on that section. Okay, so I will go fast. I've seen that many people choose 82.4% choose all of the above. I know this is the most popular answer. I see 15.7% says you need to change your mobile phase and or stationary phase, which is the correct answer. So B was the correct answer. And now we will see why. So I will go very briefly. This is the basic of chromatography. We have here on this graph three peaks. One that is time zero, T0, where we have an unretained compound, and T1, T2 are representing the retention time for two other molecules that are retained on the column. Okay, T0, we will transfer that into V0, taking account with the flow rate. And same thing with the T1 and T2, we will transfer that into V0, V1, and V2. The reason is it will be easier for all the calculation afterwards. So the definition of the retention factor, K prime or K1, K2 for the peak 1 and 2, is defined by V2, the volume it takes to elute compound 2, minus V0. So what we have here is the distance between 0 and 2. So the true volume where we have the interactions of the molecules with the stationary phase. And we divide by V0. V0 is basically, for a compound that is not retained, that volume represents the column volume. So there's no interactions. This is just how much time it took or how much volume it took to go across the column. So when we divide V2 minus V0 divided by V0, basically we are calculating how many column volumes it took to elute my compound 2. Same thing for compound 1. So this is something that we will see from now to the end of the seminar. The column volume will be extremely important terms we will use. So if we are looking at the retention factor, we calculate it like that. So in liquid chromatography, the retention is driven by the preference of the molecule with the mobile phase. So if the molecule prefers the mobile phase, if it's suitable, it will elute, it will go out. And if the molecule prefers the stationary phase, it will remain longer on the column. And what we do in the gradient, for example, we change the mobile phase to make it more attractive to the molecule, so the molecule will elute. Okay, that's very simple. Now, to increase the retention factor, we must change the mobile phase and or the stationary phase to make the mobile phase weaker for my compound, so it will prefer to stay to the stationary phase, or we make the stationary phase more attractive or more retentive. So that's the only way. Many people will use a longer column, and that's why they have inserted all of the above. A longer column will not provide you more retention. You can imagine that V0 will double if you double the column length, but the volume to elute your compound will double as well. And when you look at the ratio, you don't gain any retention. You just waste more time. Same thing for the flow rate. If you decrease the flow rate by half, V0 will double. Your retention time of your molecule will double as well. And if you look at the retention factor, it will be the same number. So that's a good thing, because for us, we know that if we keep the same mobile phase mean also same pH and same temperature, and the same stationary phase, we will keep the same retention for my compounds. One thing we will also review very quickly is the resolution. We have on the top the resolution equation. So we are looking at 2 times T2 minus T1 divided by W1 plus W2. The W1 and W2 are the peak width, and the T2, T1 are the retention time of my peak. So this is easy to calculate. And I'm showing you this because sometimes we use a calculator and we get something on a smaller particle that comes much faster. And we are used to see, like in this example, a difference of 5 minutes between my two peaks. I know that the resolution is very good. And when I look down to the other chromatogram, I see a peak that comes at 2 minutes and 3.1 minutes. And many times we are not very comfortable because we think they are too close to each other. We think visually that we have lost resolution, but if we consider the peak width, we may say that like in this example, the resolution on the upper chromatogram and the bottom chromatogram are identical. So that's the key message here. Now, for people like me that prefer to visualize this equation, it's basically the distance between the two peaks. T2 minus T1 is the blue arrow. So that's the distance between the two peaks. And the denominator is the half peak width. So the green portion of the peak. We don't use that because it's more difficult to calculate. So the equations on the top is easier, is faster, but the one on the bottom is probably more visual. So basically we want the time between T2 and T1 longer than the addition of half peak width of my two peaks. So we will have a good resolution. If we have the same length, we will have a resolution of 1, which means that my peak coelute. Okay, so now regarding the retention time and resolution, what we see very often is when we use sub 2 micron particles, we decrease the runtime, and don't be scared if you see a peak coming before 1 minute. That's very, very typical. Sometimes we have a V0 that will be 20 seconds. So when we see retention time of less than a minute, sometimes it's enough retention. It's the same as probably the other one. But I know that some people will decrease the flow rate or they will use longer column because they don't feel comfortable. But stay with me, it's the same thing. Same thing for the flow rate. Sometimes we may have to go with 10 to 13 PSI, 13,000 PSI, and that's normal. The equipment is capable of doing it, but I know that some people are more comfortable using, in the 5 to 7,000 PSI, and it's basically just for, they are used to it, but there's no physical reason not to use the 10 to 30K. It's really a question of get the calculation done and operate with those parameters and forget about the intuitive sometimes reflex that we have to decrease the flow or to use longer column when it's not necessary. Second question, what is L over dP? So again, this is something we will talk about in the next few slides, but I would like to know how many of you already know what it is. And I don't give you any details about L and dP so far. I just want to go from scratch. I won't give you too much time to answer. I will go very quickly. Okay, so that's good. We have people that says it's to select the particle size. This is true. And this is also to preserve, I forgot to mention, sorry. I forgot to mention that it was, there was two good answer, basically. So the other one is also to select the column length. So the column length and the particle size, this is what L over dP will be used to. So I'll review this very classical equations of resolution. There's three parts, the efficiency part, the selectivity and retentivity. We know that if we keep the same stationary phase, we will keep the same retentivity, we will keep the same selectivity. If we want the resolution to be the same from one column to the other column, we need to keep the efficiency constant. So we know that the efficiency is one of the term of the efficiency is N, theoretical plate, and we know that it's inversely proportional to the particle diameter, the dP, and we know it's directly proportional to the column length, L. So if we keep that ratio L over dP constant, because the two other ones are constant, our resolution will remain the same. That's the goal. To give you an example of the L over dP, I'm taking this very typical HPLC column. It's a 4.6 by 150, and it's a 5 micron particle size. We calculate the column length, particle size. We calculate the L over dP to be 30,000. Then if we want to keep the same resolution, we'll keep the same L over dp. And see here the examples. If you are using a 3.5 micron, you should use a 105 millimeter to preserve the same 30,000. Obviously, we don't sell 105 millimeter column length, so we will use a 100. And basically 28,500 is very, very close to 30,000. It won't make a very, very big difference. A slight difference, but not too much. Same thing for the 2.5. We will be able to use a 75 millimeter long to get the same resolution power, the same 30,000 L over dp. And for the 1.7 micron, we will use a 50 millimeter long to get very close to 30,000 L over dp. Okay, if I put that into a graph like this, we put the L over dp ratio on the axis and the particle size on the other axis. And we have we can see that with the 5 micron, the 150 millimeter long give me 30,000 L over dp, identical to the 3.5 by 100, 2.5 with 75, and 50 millimeter with the 1.7 micron. So now you have a choice. Depending on what you have in terms of system, you will say, okay, I can use one of those. I will get the same resolution. Okay. So let's go with the next question. When you use a smaller particle, if you want to keep similar efficiency or the resolution power, should you increase the flow rate, keep the same flow rate, or decrease the flow rate? So you have someone that is using a publication, they use let's say a 2.5 micron particle, and you want to use, because you want to use a shorter column, you want to use a 50 millimeter long, you will say, okay, I'm going to go with the 1.7 micron. Should you increase the flow rate, keep the same flow rate, or decrease the flow rate? Okay, I will just go right now. So many people said decrease the flow rate, and this is normal. We know that the powder is smaller, so we will create back pressure when we use this, and we want to decrease the flow rate because we know that the back pressure will increase a lot. That's the typical answer, but this is not the right answer. When we go to the smaller particle, we need to increase the flow rate, and I'll show you why. So this is a graph that is representing the HETP, is the height equivalent theoretical plate. The smaller the number, the more resolution you can get. Okay, I will go very, very simple. I will remove some information, some observation. There's a lot of observation we can do on this one. But basically what we are showing you here is if you use a 10 micron particle, the best resolution will be at the bottom of the curve. So it will be, if I go down, there's a linear velocity in millimeter per second, but this is not telling me anything for me. It's very, very theoretical. I will go into a column ID. I will take the 4.6 millimeter ID column. So if I take the, let me go with the pointer. If I go here where I get the maximum resolution of that particle can give me, on the 4.6, I will be roughly the 0.7 mel per minute. And we can cheat. We can go to 1 mel per minute instead, but then we will sacrifice the resolution. We will not get the best resolution. Same thing for the 5 micron. Probably the best you can get with a 5 micron will be running at 0.7 mel per minute, but then all people will go at 1 mel per minute. They will sacrifice the resolution. They won't get as much resolution, but it's not a big loss. Same thing for the 3.5. We need to go faster, and a 2.5 faster, and a 1.7 we need to go faster. If we go if we don't go as fast, if, for example, if I decide to go at that flow rate, I will not get the optimum resolution power that particle can give me. The ideal case, and now I will switch to a 2.1 millimeter ID, will be in that range, 0.6, but you have space to go to 0.7, 0.9 on small molecule. If you have larger molecule like peptides or proteins, you will need to slow down, but this is just to give you an example. Like this is with small molecule, but it will be valid for the peptides as well. It will be different curve, but it will be the same principle. So the information to retain here is, as we go with smaller particle, we need to increase the flow rate. This is the example of a 4 column packed with different particle size. So this column is, and everything is a 2.1 millimeter ID now. So I want to compare apples to apples, but they will have different length with different particle size. And you can see here that the flow rate that I'm using here on the UPLC, for example, would be 0.6 ml per minute or 600 microliters a minute on a very short column with small particles. As I go with larger particle, I will need, and longer column, I will need to decrease the flow rate. So that's the relationship I want you to remember. So now what will be the impact on the chromatography? You can see that the resolution on all of them remain similar or very, very close to each other, which is fine. Now you can imagine that using a smaller particle, using a shorter column, using a higher flow rate, you get the answer much faster with the same resolution. So here we were able to do it in 10 minutes, here in 4 minutes, here in 2 minutes, this one in 1.1 minute. And again, everything is happening before almost 1 minute, and it's okay. It's the same as having something eluting at 4 minutes. Nobody was questioning 4 minutes was good. Yeah, well, 0.45 or 0.5 is also as good. So that's one thing that people sometimes forget. Now we talk about the Acuity BEH to be equivalent to the XBridge BEH. And I will just mention something about the naming of the column. But the thing is, this one, because we are going at 600 microliters a minute with 0.7 micron, the back pressure will be the price that we will need to pay for it. That comes with the technique. We will need to have a system that operates, that is capable to operate at higher back pressure. So my limitation when I will come to say, okay, in the literature, they were using that column, let's say a sub 2 micron particle. Will you be on your system? Will you be able to use that column on your system without changing the flow rate and without cheating on things? You may say, no, I don't have the system that can go to higher back pressure. You may want to then take from the literature the information that the scientists have used and transfer that to your more practical column for your need. So this is the kind of things we will do. I always say, if you see a column used in the literature, it's not necessarily the best for you because it's not the best for your system. So very, very briefly, I'm just showing you this historical reason why we call the Acuity BEH and then we have the XBridge BEH. So it's really a question of nomenclature. We wanted to make sure when we introduce the Acuity system that nobody will use the Acuity column on the HPLC at the wrong flow rate with the wrong values and getting bad results. So we wanted to give a different names to the other BEH that can be used on the HPLC, and we call them XBridge. For the HSS and CSH, it's the Acuity HSS CSH, and in the HPLC world, we call them XSelect HSS and XSelect CSH. But again, later on, like a few years ago, we introduced a Cortex, and it was not necessary now. 20 years later, it was not necessary to distinguish between the UPLC and HPLC. People know that a 1.6 micron is a UPLC kind of particle, and a 2.7 or 5 micron are more suitable for UHPLC system and HPLC system, right? Another question, what is the dispersion? Dispersion is a value that we see in microliter, and I would like to know if is it a measurement of a peak volume in a set experiment? Is it a system void volume? Is it the system volume from the injector to the detector? Or is it the same as a system dwell volume? What is dispersion? It's a tough question, but again, I will explain what it is in the next slides. Okay, thank you. So now we see more or different answers because it's not a clear term. Dispersion, I hear it very often, and it's not exactly appropriate. So it will be a good thing to cover. It's not a system dwell volume. We will explain what it is. It's not the volume from the injector to the detector. It's a good answer. It's a very, very popular answer all the time. And it's not the system void volume. It is the peak volume in a set experiment. And I'll show you what it is. Okay, imagine this is a very, very basic system where you have mobile phase, the pump, and you have the injector to the detector. So we are interested to look at what happened to my sample from the injector to the detector. But what I measure is not the volume of the tubing. It's not that volume. So that answer was, I understand, a good try, but it's not the case. So as we inject the sample, we start to have a dilution. The peak becomes a little bit larger. So you can imagine in the tubing, when it arrived to the column, I want to have the narrowest band as possible. If we start to dilute, we start to have larger band. Now in a gradient, I can understand we will refocus at the end of the column, but this is still contributing to the dilution, certainly after the column to the detector. So basically, there's a dispersion inside the column that is necessary. We cannot avoid it, but everything that happens after that will need to be considered. So basically, we take a peak. We take the peak width at 4 sigma, so that value over there, and we just multiply by the flow rate, and this will give us the dispersion value. And basically, it's not important to calculate it. It's important to be aware. If you are looking at your system and if you calculate the dispersion, you will know what to expect in terms of column to select. So the experiment is we inject 1 microliter, and this is what we get. On the UPLC H-class, that 1 microliters is now into a 7 microliter band here, from here to there. If I use another system, I may get like 34 microliters on the Alliance. So my 1 microliter is now large like this, and this volume is represent 34 microliters. So you can imagine now that if you are using a column that is a 2.1 by 50 millimeter, it's only 1 70 microliters. That's the column volume. You can imagine that when you have a dispersion of 34 microliters, it will really make a very, very bad chromatography. So it's not a good choice to use a 2.1 by 50 on the Alliance system. It's not a good choice. We will need to go with a wider column ID, so the dispersion will not look bad. Again, everything is relative to the column. We will talk about this one. Now, we have the HPLC that will be typically, that will have like 40 microliters dispersion. We will have the medium dispersion system that will be between 20 to 30 microliters. And we will have the low dispersion system that will be less than 20 microliters. You don't need to get the exact value, but having an idea of what it is. Now, I will start with the UPLC. You can easily use a 2.1 millimeter ID or even a 1 millimeter ID if it's a long column. If it's a short column, you can use a 2.1 easily because the column volume, as we mentioned, 2.1 by 50 will be 170. So 20 microliters is not as bad as if you were using an HPLC. So on the HPLC, I will use larger column diameter. I will use larger particle because of the back pressure. And in the middle here, in the medium dispersion, I can use a 2 point something micron, and I will be able to use 3 millimeter or 2.1 if it's a long column, or 3 millimeter if it's a short column. This is where you will get best results. I'm showing you here the example when we are using a small column volume here, the 2.1 by 50. On the HPLC, we barely see the peaks. It's very, very bad. On the UHPLC, a medium dispersion, it will not be very good. And on the UPLC, it will be good. So imagine that you read the article, they get this result, but you have that system and you get this result. That's the kind of things that doesn't work. Same thing here as we go with the larger column ID and larger volume, a longer column, larger diameters, we get better results. And then for the HPLC, it's really better to use a 4.6 millimeter, even if it's a short column, to get good results. Okay. Yeah, so we will avoid those situations. So now, in terms of column selection, I can say that, okay, from the original method that I saw in the publication, I will keep the same stationary phase, whatever it is. I will calculate the L over dP to select the particle size that will be appropriate with the flow rate that will be appropriate for my system, for the back pressure limit that you have on your system. And then you will select the column ID to match the system dispersion. High dispersion, high column ID. Low dispersion, you can go with lower, smaller column ID and save solvent. Okay, so that's good for the column. Now let's look into the system. In the publication, they can use a binary system or they can use a quaternary system. So a binary system is you have two pumps that will mix at high pressure the solvent, and then you will go through the detector and it will hit the column, the head of the column after a certain delay. If they use a quaternary system, the blend of the solvent will be done before the pump, so it will be done at low pressure. The mix where the formation is done will go through the pump, so the pump heads and everything. Then it will go to the injector, will go to the head of the column. You can imagine that this is a bigger volume. So that's the dwell volume definition. It's from the gradient formation to the head of the column. So that's a huge volume. So this will be very important to consider in our method transfer. And the reason is, as you can see here in black, we program this change of of gradient, the starting gradient at 5 minutes, but there will be a delay because we will need to consider the system dwell volume before we reach the column. So in the red, we see what it is. Then there's a couple of calculations we need to do to make sure that we get the proper measurement of that dwell volume. It's all defined in the help of the calculator as well. So I won't go into details in that. So again, here, just to give you some example, the Align system, the HPLC system is a quaternary system, looks like this. The dwell volume will be around 1.1, and it's good to measure it with precision for this one because this value, unlike the dispersion, this value will be important when we do the method transfer. And then we have a couple of others that will be binary, quaternary system. We have the UHPLC H class and I class. So you can see that the H class plus will be 0.3 mel, and this one will be 0.1 mel, and this one will be 0.07 mel. But again, these are just to give you some ideas of what you should get, and when you calculate it, you should be close to those values. In the worst case scenario, you can use those values. Okay. So the importance of it is that in the publication, if they were using a UPLC, they were having that delay, and now if you are using a HPLC, you will get that delay. So we need to go to calculate the difference between the two. We need to consider that in our calculation, and we'll see that. Okay, end of the theory. We have seen the dwell volume, the dispersion. We have seen everything else. Let's go back with a real example. Now, what I would like you to remember, we will go from a UPLC separation, something that we found in the literature, and we would like to use it on our column, on our system. In this case, just for the calculation, just to show you how far we can go, I will transfer that method to a prep column. So a big column with larger particles and everything, just to show you that it still works, whatever we change. So we have a BEHC18. It's a 1.7 micron, 2.1 by 50 millimeter. We are running at 1 ml per minute, and we are injecting 2 microliters. Okay, this is the chromatography that we get, 5 peaks that are well separated. We are satisfied with that separation. That's something we would like to reproduce on the prep system, on the prep column. So, the first thing to do is to look at the L over DP ratio. So we were using a 50 millimeter with 1.7 micron. We get 30,000 L over DP ratio. And we have these two choices. Either we can go with a 3.5 by 100 millimeter long or 5 micron with 150 millimeter long. If you are in the lab, you are looking for the throughput, you will probably try to go on this one. In the case of a prep column, because we want to isolate as much product as possible in one injection, we want to go with the column that has the largest volume, because we will be able to isolate more compounds. So in this case, we picked the 5 micron by 150 millimeter long, which has more capacity to load than the other one. And we have picked the 19 millimeter ID. And this ID is selected from the limitation of the flow rate of my pump. Some pump can go to 150 ml per minute. Some other pump can go to only 40 ml per minute. So this is a limitation into the column dimension that we have. But again, it will still work on this one. Okay, we have these equations, like what the flow rate will be on my method. So the optimum flow rate, what will be the optimum flow rate on my prep column. I don't want to give you all the details, but typically if I was using 1 ml per minute on my 2.1 millimeter ID column, I will need to use 27.8 ml per minute on my 19 millimeter preparative column. Okay, so from 1 to 27.8. Remember that 27.8. Now for the injection, I was injecting 2 microliters on my small columns. I will be able to inject almost 500 microliters on my 19 by 150. So that will be the equivalent volume. Just to give you an idea, we have sometimes in the Carrier News manual, we will give you some internal diameter and column length. So we will give you the column volumes for them. It's okay to use the formula. The only thing I will ask you is to keep the same formula for the 2 columns you will measure. So some people will use you can use a calculator, by the way, to measure it, but you can also calculate it by the empty cylinder. So the L, the length of the column, multiplied by the surface, PR square, and you will get, don't forget the units and everything, you'll be able to get the volume of the column. In our case, the 19 by 150 millimeter column has 42 milliliter in volume. So that's a huge, huge column compared to my other one that was 170 microliters. Okay. Now, what will be the impact? You remember we talked about the dwell volume that we have measured. So we will convert that dwell volume in terms of number of column volumes. So imagine that the dwell volume, let's take this example that we just gave a second ago. I was using a 2.1 by 50, so it's 170 microliter. So imagine my dwell volume was 340 microliters. So I will say that was representing my 2 column volume. If I transfer to another column and my column is bigger, maybe my column volume will be 340 in this example, and my 340 microliter of dwell volume will be just 1 column volume. So to be equivalent, I want to mimic that same 2 column volume here, I will need to add another column volume. I will need to go with a hold to compensate for the time. So they will hit the column at the same time. Similarly, if you have maybe a smaller column, or if you use a system that has more dwell volume, you may face that conditions where the dwell volume will be representing 3 columns volumes. So if the initial column, the initial method was using 2 column volume, you will need to use a function that will inject your sample before you start the gradient. So basically, in this case, you would inject after 1 column volume, and then you will do that. So that's what the calculator is doing, in fact. Give you some example here. This is a column calculator. So we have here the dwell volume. We have put 1.2 just for fun, 1.1 just to give you an example. And we are using the same column. So it was a 4.6 by 75. This is a 1 column volume. It's the same column on the other side. So it will be the same column volume, but I don't have the same system. But you see now that I will need to add 100 microliters to compensate for the difference in dwell volume. So my time will be either what we do typically is we will add the time in my table. So in my table, I will add the 0.1 to the isocratic initial condition. So that will be mimicking, it will compensate for the dwell time difference on my 2 systems. Okay. Now, if we are using a different column, I'm using the same 2 systems. I mean, the 1.2 and the 1.1 in terms of dwell volumes. So that's the same as the previous one. But now I'm using a column that is twice as long. So many people will say, well, we just have to double the time here. So the 5 minute becomes 10 minutes. My 11 minute here become 22 minutes. That's right. But my dwell volume here, if it was, one or 2 column volume here, it will be half of a column volume because my volume is extremely high. So in this case, I will need to compensate. I will need to add the 1.3 microliters delay to mimic the same number of column volume for my dwell volume here. It sounds complex, but stay with me. You will see the examples later. You don't need to remember all of that. Just to be aware that you need to compensate for that, and the system will compensate for you. You don't need to do anything. Now, for the system volume, now we will look into the UPLC system that we were using initially. So we have calculated the system, the dwell volume, in terms of column volumes. So you can see that this is the dwell volume of my system that we have measured, and this is the column volume. So my dwell volume represents 0.6% of my column volume, so 0.618 column volume. And here I do the same with the autopurification system. You see I have a huge column here of 42 milliliter, but my system is a prep system, has 2.6 ml. But 2.6 ml relative to 42 is 0.06%. So I have a very, very small dwell volume compared to the other one. So the number here is bigger than here, but my column, relative to my column, I jumped. And that's why I have a difference here. So the difference is calculated. I will go with the initial time. I will go with the flow rate that I was using, the volume that I need to compensate, and this will be the time I will need to add in my table. Again, the calculator will do everything for you, but you understand where it comes from. So in my table, I will add that 0.83. Now I'm looking at the gradient table that I was using on the UPLC column. And for each of the gradient step, I will look at the duration of my segment. So it's 2 minutes. I was running at 1 mil per minute. So I use 2 ml in that segment, and I divide by my column volume. So 2 ml represent 11.55 column volume. So on this step, on the next step, I use 5.77 column volume. And again, we know each of the segment duration in terms of column volume, and this is what we will need to keep constant when we will use a calculator. This is what the calculator will do for us. Okay, so remember that 0.83 that we have add the initial old. We are running at 27.8 mil per minute. I want to do my 11.55 column duration, segment duration. So I will have in time that much, and I will just go back and calculate that time over there. So it's a back calculation. You can see all the values here that we have done. Everything is written here, so I don't need to go through it. But basically, we do a back calculation from here to get that answer over there. Okay? And then we do the same for all the gradient segments. So the initial column, the initial conditions were that much, and then the newest one are like this. So we have scaled the flow rate, and we have scaled the time appropriately. We have incorporated our initial old, and we have the same chromatography. So this is what it looks like on the UPLC system. This is what it looks like on the PREP system. So we have been able to preserve the same resolution. We have been able to proceed to convert everything properly. Good. I will go with the to improve the throughput. Sometimes we may say, okay, let's sacrifice some resolution. Like in this case over there, it was probably not necessary to have that much resolution in my peak. I realized that maybe I can get something shorter, like this one is taking 27 minutes. Maybe I would like to short this, or I would like to increase my throughput by using a shorter column. Obviously, my L over DP will not be the same, will be half of it, so I will lose resolution, but that's okay. I will use less mobile phase, I will have less back pressure, I will be able to inject more sample. That's what we want. So let's say instead to use 27.8, we will use 30 millimeter as well. So we will try to cheat two ways. But the goal is we use a calculator and it gives us the same thing, the same number, the same segment duration, and the same number column volume per segment. And we come with this different time. So it's much faster. Obviously, the peaks are a little bit larger. We have lost some resolution, not too bad. Are you there?
We can hear you, Guy.
You're back. You're back now. You froze for a little bit, unfortunately, but you can continue now if you're back online.
Okay. At that slide or before?
Slide 54.
$5.54. Okay, so that okay, I will not repeat everything. I'm sorry for this interruption. We were going to a column, but we have decided to go with a shorter one with increased flow rate. So the calculator is capable to give you the appropriate value to still keep the same kind of separation, because we have not changed the mobile phase and the particles type, but we have a faster, so we have lost in resolution, but that's okay. That's exactly what we wanted. We wanted to get more throughput in this case. Here we go. So you will say sometimes we look into the publication, they don't refer to the dwell volume in the publication. And this is where it's a little bit more difficult to transfer the method to your system because you don't know the initial value of the dwell volume. It is certainly feasible if you have your R&D department that can measure that dwell volume and can give that to the other instrument that you will use in the production. But if you can see, like in this publication that I saw in the Journal of Chromatography a few years ago, they were using a method where they were publishing the dwell volume. So they said the dwell volume of our system was 400 microliters. And they said the optimum conditions were determined, blah, 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 using this column with these dimensions, with all the information about it. And see the next paragraph here. They said we have been able to transfer to the HPLC conditions with the similar column, obviously the CSH, the XLX CSH C18, with different dimension, column dimension, different particle size, without any further development. So they add the dwell volume. They have been able to use the calculator to transfer to another column, and it worked very, very well. So they don't need to redevelop anything. Okay, so this is the calculator. We have the options to use the porous or fully, not fully porous. You can have also the unit. You can, if you prefer to use bar, Pascal, and the other one is PSI, obviously. So you can look on that. That's one thing. And all the help, as I was showing you before, all the calculation, it's all written there. So you know where it comes from. So how do we calculate that? And also for the dispersion and the dwell volume. And I would say have fun with it. One way I use the calculator very often is to predict, like, okay, the publication is using this column, and can I propose the 2.5 millimeter particle ID with 75 long to preserve the same L over dP, like in this case it was 30,000. Can I propose this? And if the limitation of the system was 4,000 psi, I know that this one will be exceeding the back pressure. So I will need to say, no, let's go with a 3.5 instead with 100 millimeter long to preserve the same 30,000 L over dP. And then the back pressure will be lower. So that will be the column I will recommend to use. Okay. There's a lot of information that will become available as the new version will become loaded, but you can find some information in the white paper over there. There's a couple of things you need to know. Sometimes it won't work because sometimes it depends on the temperature system. You have active heater, you have passive, and depending on the system that you have, maybe the temperature value that you see in the publication is not the same temperature that you need to put in your system to mimic the same thing. But I mean, it will give you a very, very good, a good first method to try because it's working very, very well. So I think that we have done the tour. I wish you will be very successful by selecting the appropriate column for your separation on your system. And if you have any questions on that, if you are using it and if it doesn't work, please contact us. We will try to find out what's the problem or how we can help you best. Thank you very much, everyone.
Thank you, Guy. This is an outstanding presentation. Lots of details covered here. I want to get to the Q&A because this was a long webinar, and I did get a few questions coming through, so I'll go ahead and start those so we could try to wrap this up in a couple of minutes here. And if we don't get to your question, don't worry, we'll definitely respond to you offline. First question, where can I find the volume of my columns?
Well, you can measure it. You can take as long as you keep the same method. You can. This is what I do. This is what I do many times. It's not important to know if there's packing material in it. If it's not, what's the compressibility or what's. No, it's really a question of you have the cylinder. You can take the length of the column multiplied by the surface, PR square. And then you get the volume you compare to the other one, so you will get the good value of the column volume, basically.
Okay,
or
thank you.
in your calculator, you can tweak the time to get the number of column volume per segment. So you will try to get one. So you will just put, for example, 1 mil per minute. The flow rate is not important in this case, 1 mil per minute. You will put the column dimension, and you will say, I would like to see in my table 1 column volume into my segment. And then you will be able, with the flow rate, to see the duration, the time, how much was the column volume.
Okay, good. Next question. I use different curves in my method. How do they transfer?
Yeah, yes, for those who have a water systems, you can use curve 1 to 11. You keep them in your method. It's not mentioned here, but it's included if you have a method 6. And basically, that's one reason when we say it's to transfer a method from one system to almost all system. Obviously, if you have a curve 4 or 7 in your in the publication, if you don't have a system that has the capability to make those curves, it won't be possible for you. It will be more tricky, more difficult. You can have the time separation, but the what you have in between might be difficult. But if you have a waters to another waters, they use curves, you enter the same curves. Very good question.
Another question. We have a couple more that we have time for. What if I don't know the system dwell volume of the original method?
Yeah, that's a tough one. You have to estimate based on probably some of the value that I gave in the seminar. That will be the best one you can do, and that may sometimes explain why we like if someone have tricked their system, if they have used a system that is known to have 300 microliters of dwell volume, but they have changed the tubing, they have used something exotic, they are doing post injections or post column infusion, whatever, and they have changed that volume, it may become more difficult to do. But if you go from your lab to and you know the system that you're using, you can measure it. That would be the best way to do, obviously.
Okay, thank you. Another question here. Can I use your calculator if I mix 3 mobile phases?
Yes, I probably went too fast, but the calculator, you can have a binary. So you will see composition A and B, or you can go with the quaternary. So you will see A, B, C, D, 4 different solvents you can put in them. And obviously, you will use this one if you have to mix 3 solvent. But the calculator is capable of dealing with 3 solvents or 4 solvents.
Okay. Does it work for HILIC methods? Hopefully I asked that properly.
The ILIC, yes, yes. We have seen some examples on the reverse phase, but it's exactly the same principles with the ILIC, with the particularity of the ILIC in terms of needle wash and stuff like that. You need to be careful about the sample diluent, stuff like that. But in terms of the transfer of your method, it will be the same principle. Yes, it works.
Okay, super. A couple more here, and then we're going to wrap it up. Are all particles scaled up?
Okay, if you go, yeah, okay. I saw one example where a customer was using a different particle that was not a waters particle. This is something that we do, and I remember a long time ago, people were saying, "Oh, we have developed a 1.7 micron, we have a 2.5, we have a 3.5, we have 5 micron particles scalable," and I was wondering, why do you need to mention it's scalable? Until I get into a case where the customer was using another particle from another vendor, and it was, I won't say the dimension, it may plug the competitor, but they have tried a different dimension. It was exactly the same thing. I was with the person, the system, we had everything, and so the R&D was using one column. The other ones, we were able to calculate the dwell volume and everything. We put everything on our side, and we found that it was not scalable. And then I said, okay, now I realize the importance of that terms. But if you see the publication is using a waters column, Cortex, XBridge, or whatever, it is scalable. Yeah, that's a good question.
Okay, great. I think we got time for one more, Guy, and I will wrap it up. But I saw the preparative OBD column calculator on your website. Is this the same?
Yeah, no, it's not the same. We have one specifically for the mass transfer and everything. It's more, yeah, it's there. But again, in few weeks, you will see the Acuity column calculator. That's the one you will need to download. It's free, and you will just need to use it. It's very, very interesting. and you will find it very useful for many, many things that you do in the lab.
That's great. If we have a chance on our follow-up emails, perhaps we can include that link for those that have participated or those that had registered to attend. But I think we need to wrap it up. It was a super great webinar with lots of content, Guy. I hope the audience was as pleased as I was to hear and listen. And hopefully they'll participate in our upcoming next webinar, part 3, to be announced sometime in November. So thank you, everyone, for your attendance. And thank you, Guy. Have a wonderful rest of your day. Thank you.
Thank you very much, everyone. Bye.